So Bayesian statistics in a 10-minute lightning talk with the microphone on.
I don't think I can do this in 10 minutes, but I'm up for the challenge. The good news is this is something that is completely and totally impractical and of no use to you in any real way. So they cut me short. You won't really miss anything. So what prompted this is a library that Rasmus Bach released in December 31st of last year. And it is a library that does Markov Chain Monte Carlo in JavaScript, which means you can do it in a browser or Node.js or whatever. And for those of you who say, what the heck is Markov Chain Monte Carlo? It is really one of the foundational algorithms, actually it's a set of algorithms, for Bayesian statistics. And it's a relatively new development in mathematics. It actually originally came out of the Manhattan Project in World War II, where the smart folks building atomic bombs needed to develop some algorithms, and they did. And they built bombs with them, I guess. And it was several decades after that some statisticians looked at that and said, hey, those algorithms that they use, those can solve a really big problem that we have with Bayesian statistical inference. And mainly the problem was they couldn't do the math. Bayesian statistics, if you haven't seen it, don't worry too much about the details. But it's really easy to understand conceptually. But if you try to do it for any real problems, the math just blows up when you can't do the math. The integrals are not solvable. And thankfully, today, in addition to screensavers, we have computers. And computers can do things that people can't do. Namely, they can run numbers lots and lots of times. And Markov Chain Monte Carlo is a numerical approach for solving some integrals that couldn't otherwise be solved. And with that, we can do Bayesian statistics. Now, I said this isn't practical, and you're wondering, well, isn't Bayesian statistics practical? Well, yeah, absolutely. Bayesian statistics is definitely practical. But the problem is, any real-world problem, people are going to use special-purpose development environments, programming languages. They're called probabilistic programming languages, and there are several of them. And even with those special languages, which are generally written in like C or C++, on a desktop computer with lots of cores, you can run hours to get an answer. And clearly, you're not going to do that in a web browser, right? So this library is only good for kind of toy problems to play around with. But for those of you who know me, you know I like to visualize stuff. And the browser is a great place to visualize something. So I thought, well, this is cool. I can't solve a real problem with this, but I can use this library to kind of visualize how Markov Chain Monte Carlo actually works. So that's what I put together. And if you go to my website, JSDataViz, that's it. The place you want to look for this is in the visualization section. And it is the very first one, Markov Chain Monte Carlo, very top, until I write another post. So for this one, I set up a little toy problem. The toy problem is pretty simple. We have a population, and we're interested in measuring some value of that population. So for example, it could be adult US males is our population, and we're interested in the average height of adult US males. Now, we clearly can't go measure the height of every adult male in the US. That would take too long. So a statistical technique is we sample. We maybe get the first 10 people that are US males, measure their height, and then say, well, we know the height of 10 members of the population. We'd like to estimate from those 10 measurements what the height for the entire population is. So that's the type of problem I have set up here. And when you start the problem, you will have to hypothesize a distribution for the parameter that you're interested in this case, height. And we'll say we believe that height is going to be distributed according to the normal distribution, otherwise known as the Gaussian distribution, or the bell curve, that kind of thing. And therefore, it's going to have a mean and a standard deviation. We don't know what those are. That's what we're interested in estimating, but we'll stipulate that the thing we're measuring has a mean and a standard deviation. Well, that's two parameters that we want to estimate from the measurements that we have. And two parameters work nice in a two-dimensional graph. Now, in the real world, I said in the real world, you have lots more things to do. Computations are much more complicated. In a real world, you may be working with thousands of dimensions. So clearly, we can't really visualize a 1,000-dimensional thing, but we can do 2 dimensions, and that's what we've got here. What I've drawn is, in the x-axis, from 0 to 200, I say our mean value is somewhere between 0 to 200. That's our guess. And the standard deviation is somewhere between 0 and 20. And I cheated too, I'll tell you this. I actually know the mean and the standard deviation of this particular population because I constructed it. And in particular, I said, I want a population where the mean is 100 and the standard deviation is 10, which, guess what? Mean of 100, standard deviation of 10, you're right there. But I'm not going to tell the algorithm that. I'm going to keep it a secret. And the idea is the algorithm will give us an estimate that we hope will be reasonably close to that value. So how does the algorithm work? Markov Chain Monte Carlo, Markov Chain part means that it's incremental. It advances one step at a time. And each step is only concerned with the previous step. Doesn't have a lot of memory to it. And Monte Carlo, yes, it comes from the gambling casinos of Monte Carlo. It means it's all random. And that also means that when I did a demo, it might not work. You're right, because it is random, so there may be the 1 in a million chance this thing's going to blow up, in which case I'll just leave quietly and see me out the door. But what it will do, when we start the algorithm, it's going to take just basically a wild-ass guess. I don't know what the mean is, I don't know what the standard deviation is, so I'm just going to pick a random value out of the air. And that's what I'll start with. And then I'm going to start iterating. And in each step in the iteration, the algorithm is going to move a little bit different for each of those values, a random amount. So it's going to add or subtract a small random amount to its guess for the mean, and a small random amount to its guess for the standard deviation. And that'll give a new guess. And it's going to compare the new guess with the old guess. And if the new guess is more consistent with the data that it has, those 10 measurements that we start off with, if the new guess is more consistent, then it's going to tend to go to the new guess, to use the new guess. Not always, but it will tend to go that way. And conversely, if the new guess is less consistent with the data, then it's going to tend to stick with the old one. And it's just going to keep iterating over and over again. So let me get this started. And this is the starting point it picked at random. And it's not actually going really close to the red dot. There's maybe 1 in a million chance. But I have my faith. So each of the values that it's plotting, it's still going. It just kind of went off the screen there. Maybe it'll come back. But, there it is. There. It's coming back. Now, when you do a Markov Chain Monte Carlo, you actually don't care about typically the first 1,000 or so iterations. Because as you can see, it takes the algorithm a while to get up steam, to get past its startup, which could be a really awful guess. And so when you implement this in the real world, you'll throw away, in my case, I'm ignoring the first 400 guesses, and those were in green. And I can see it's already switched to orange. And I'm going to run, in this particular demo, 600 more iterations, and those are in orange. And those ones are going to count. And you can see that it is kind of sticking pretty close to the actual value. Now, Markov Chain Monte Carlo doesn't converge on the real value, so you're not going to see it home in on the red dot there. But instead, what you do is add the values that you count, like the last 600 here, those will tend to be near the actual value. So if you want to know, if you want to have a guess for the mean, when all this algorithm is finally done, it's gone through its 1,000 guesses, 1,000 iterations, take the last 600 values, each of those will have a guess for the mean, and take the average of those. And say, well, that's probably what my mean is. And do the same thing for standard deviation, and there you go. In this case, the average for the mean was 105, and standard deviation was 8, which is close to the actual population of 110. And that is how Markov Chain Monte Carlo works. And if you want to read a lot about it, including math, I have a fairly lengthy post that you can go through, and then somewhere down here, after I get through talking about math, there's the source code for it, and the source code is commented as well. So you can see how this little library implements Markov Chain Monte Carlo. Did I make it in 10 minutes? All right, thank you much.